Yes, for today I brought you more landscapes, more L systems. Good morning, with a long name. um, yeah, so I was just wondering. I mean, there are so many things I really want to do for this lecture, like writing a book about it. That would be really awesome because I really like the topic. But anyway, what I actually wanted to do was to present you the whole terrain stuff in 3D. But that actually is a problem, also because of the choice of the tool. Sorry, I had to put stuff away from my desk. Um, because P5 chess is really slow. I mean, it's really slow. It's really buggy. It's very nice in that sense that you can do stuff. But yeah, it's like programming Unreal Tournament in Scratch. So it's not fitting for that. But I tried to do at least something. Wait, there is this triangle to height map thingy, which I wanted to give you. Let's see. Yeah, that's basically where I wanted to start today. So what I wanted was I actually wanted that last year too, and I didn't get around to actually implement it in 3GS. So we had these height maps. You remember the height maps? Wait, I can create a height map. Where is it? Thermal erosion inverse. That one is a nice one. Yeah, create a height map for you. So we have these height maps, and these actually denote the height of a point. Like the white ones would be up there, the black ones would be down, and if you look at it from the side, it should give you a landscape. So that's the whole idea. And the good or the crazy cool thing about it would be to sample points on a rectangular, actually give you a triangulated version which shows the whole thing in 3D. And the approach would be to actually sample points on a rectangular grid. And the finer the grid, the more triangles you have. And then you create the triangles with the sampled points. So that actually sounds good. There is more to triangulation, of course, than that. For instance, it would be cool not to have a rectangular grid, but to move the points around a little bit because they're triangles anyway, so that they actually sit on the peaks or something like that, that don't smooth it out too much. Yeah, P5 chess has a lot of bugs like vertex colors and those strokes eat up CPU like crazy. So, and WebGL is really slow, and while everything is slow, also the lighting is awkward. But what I wanted to show you is that it works in a way. Let's put this one here. For these things, I actually switched from the browser to a real IDE. Let's go there. Let map to boxes. Let's use this one. That would be the start file. Why doesn't it work? Try it this way. It doesn't work. It always worked. No, it doesn't work anymore. View, active editor, no. Increase font size, yes. View, active editor, increase font size. Yeah, now the font is a little bit bigger. Maybe once more. View, active editor, increase font size, yes. I don't know why it doesn't work with just rolling it up and down. And of course it doesn't translate here. Delete it. No, shift. No, I don't know. Crazy. They changed it. Yeah, so what I wanted to do is I have this resolution here, 50 by 50. I create some noise that's here. I have the camera, and now I'm actually putting boxes in there because boxes are faster to render actually. So I move around in these steps and then see what the height is, and then basically put the boxes here, like the size of the box, scale it in Z, so upward, and that looks like that. I haven't used it for so long. looks like that. So there are a lot of boxes. And they basically give us a height map sorts. So that is the high performance thingy. We can fool around with it if we have fun, like 25 and 25. Let's see if it still works. And of course it will open it up here. Oh, of course it doesn't work. Very bad programming from my side. Let's change it back. But what I actually wanted to do is to have these triangulated versions. So instead of painting boxes here, and now I think it's really bad that all my shortcuts do not work anymore. I don't know why. So now we're going through this grid, and actually we're painting per. Let's set this one up. Yeah, now see it's really early. Not only that I'm boring you with source code, but also I'm not really prepared. Let's see what the screen did. Oh no, it's not so bad. It's still here. Stream is still here. Awesome. So what I actually wanted to show you now is that I can actually paint. But let's see if the Microsoft whiteboard is actually, I mean, what can you do wrong with a whiteboard? Basically ask Microsoft, you're really good at that. So it's beyond painting. I would definitely use Fresco, but I mean, that's completely an overhead here. I'll have to click 4,000 times to actually get this one running. And here we are. So I'm painting a grid basically on the height map. And for each of those points, I'm sampling the height. So the red ones are actually the heights. And now I'm taking green, and what I then actually do is I'm drawing triangles. Oh, this is not green. What is that? Oh, that's nice. It's an effect thingy. Nice. Really crazy. So I would create one triangle here. I would create another triangle here. I would create one triangle here and another triangle here and here and here and so on. And then I triangulate the whole thing. So that's the great idea. And that's actually what I'm doing here, the vertices. That's the Z scale. That's the one I get from my height map. And what does it look like? Height map to triangles. It would look like something like that. Not so bad, isn't it? I mean, the lighting is not good. And it would be easier to see it with the strokes. But yeah, well, as I said, the strokes actually eat up the CPU like crazy. We can still have fun and try it, of course. No stroke. Remove that one. And maybe I remember a shortcut, Alt F2. No, it doesn't work. Again, it does not work. I really like it. I really like my IntelliJ idea because it changed so much. Okay, and now you see it kind of doesn't go so fluently. I'm not sure if you can see it on the screen, but it gives us a height map of the terrain. Very nice. Okay, remove this one back here. And what I then wanted to show you actually is totally in my way. I need a bigger screen. Definitely need a bigger screen. Might have heard that at some point from several people, but I definitely need a bigger screen. So what I actually wanted to show you, what I'm shooting for is this inverse thermal erosion 3D. So you remember, English is today very hard for me. Remember the inverse thermal erosion? I already had it up there, but what I actually wanted to show you is this one. It's a 3D version of the inverse thermal erosion, and this one actually is animated by the erosion steps. You wouldn't see them right now, but I'm hitting a 5 and maybe you can see it now. Fooling around a little bit, hitting a 5 once more. It changes. If I move in here, much. It's flattening out stuff. Okay, as you can see, it gets from kind of rough to less rough. So what is the problem with something is definitely changing. Thank you very much. Yeah, you can actually, what you can do is you can take a look at GitHub and then run it from there. I'm not sure. I actually have to check. Wait, I'll check that. I'll check that. So I'm not hiding my source code, definitely not. Oh, GitHub does look different. Everything does look different when I'm looking at it. Can they please stop changing stuff? It's like, you know, GitHub is now owned by Microsoft, and Microsoft keeps changing Word. And my computer is getting faster and faster, and Word is still getting slower and slower and slower. And it's looking differently all the time. So they came from buttons to ribbons and so on and so on. Really bad. Okay, so let's see it here. Oh, that was the other one. So it's the link is on the web page. It's from last year, but I didn't change it too much. So let's just use that PCG. And there in the landscape stuff, there would be the inverse thermal erosion 3D. You can access the source code. And if you totally remember where it is, like, can I copy it over? Yes. Then I can show you the trick here. Open it up to me, yes. And let's see if that works. Yes. Now you can use the link online. The beauty of adding bloated, absolutely, yes. Let's just pray GitHub won't be Office 365. Yeah, but I changed the name. I don't know. Isn't it Office Online right now? Yeah, so you can access it on your own and take a look at the triangles moving around. So of course, those of you who are totally into inverse thermal erosion, if you even remember it from last week, then you might say, oh, it is not supposed to be hills. It's supposed to be plateaus and steep cliffs. And I'll say to you, you're totally right. And that's the problem of triangulation here. So what we can actually fool around with is we can actually change the resolution. That should be in the sketch thingy here. Where's the resolution? Here, 50 by 50. We can set it up to 100 by 100. Then we have a lot more triangles, and we'll also have a lot more fun. And then we can hope that we can see the plateaus and the steep cliffs. Yeah, and there is some indication of steeper cliffs than we actually thought, but it's only if it's a good match here. And the plateaus are not really plateau-y. Start it once more. But that would be on a rectangular grid, the effect of the thermal erosion. We can actually make it higher. Let's make it higher. Where's C scale? Here, 10. Let's make it 25. And go here, here, move it here. And now we have hilly hills. Yeah. Now it's looking steeper at least. Yeah, but you get the idea. there can be much more on that, like much better triangulation. For instance, moving those pointed extremums or at the borders of stuff. So that's actually cool. So Mihak has a question. Sorry, but a quick question. Is exercise 3 out because I don't see the relevant slides on the website? I totally have to check that. Where do I have? I'm putting the slides in here so that you don't have to look at the source code all the time. Checking the web page. Course, yes. Exercise. Shift F5. Oh my god, did I forget to push the web page? That might still be the case. Open my web page here. No, maybe I forgot to put in the slides, but slides are still missing. What's wrong? Okay, I have to update the slides. Thank you, Mihawk. I didn't think that I forgot this one. This should actually be solved in a second, but I'll do it later after the stream. Thank you for putting that up. Yeah, I also thought I'd shared it. I should have shared the slides. I'm not sure. This is also Microsoft. I switched to Visual Studio Code and now nothing is like I want it to be. Oh, yes, it's here. Oh, I think I know what the problem is. So I changed everything. I committed everything, I think. There's still one unsaved file. I don't know which one. Oh. Still one unsaved file. This one? I don't know. And actually it should update my webpage. I'll check that. The problem is not me changing the website. The problem is the server downloading a new version of the website. Yeah. That's a big thing. Thank you very much for pointing that out. Okay, got me in the morning here with that. But yeah, that's something I really wanted to do, like showing you what you can do with these height maps and having animated erosion and stuff like that. But yeah, I actually have to do it in 3GS or Babylon to actually show it to you. And maybe I'll do that for the XR demo. I'm totally up to it. Okay, anyway, go back to the erosion thingy. We had the thermal erosion. What we actually want to do today is the hydraulic erosion. Loading. The hydraulic erosion. So thermal erosion is heating up stuff, then it cools. Then it heats up again, and then it cools again. And while this is actually a thing that involves a lot of water, the water is not modeled. So we still have that. I've heard there are in the news there are several boulders coming down and blocking streets in Carinthia. That'd be thermal erosion, and this is rather uncommon that at this time of the year we actually have so much water and not so much cold. There would be less water and more cold typically, or less temperature and less water, something like that. It's double less. And with hydraulic erosion, you bring into this formula, you bring the water, but in a way that it's not freezing and warming up again, but rainwater washing soil down somewhere, okay? So, is there a good example of that? Yeah. It's not that bad with the water in Carinthia, you just have to... Yes, Saxonta is right, if you own a boat, you're totally okay. Yeah, but on the other hand, the water brings in if everything is wet, it doesn't get more comfortable. Let's put it that way. So I recently read a very nice novel on there is this climate science fiction. I don't know if you know that. So I'm verging off Monday morning. I'm verging off the topic. There is I don't know. There's a special name about that. It's I forgot it actually. We look it up. It's not climate fiction. It's climate. Well, it's true. It's climate fiction. That's it. Climate fiction. It is. Now it opened up on this side, so two browsers never know where it is. So there's this nice climate fiction novel. I forgot what it was called. Like something like Sky. And there was this person living in Florida, and they had a beach house. Now they had a water house, and they had to go there by boat. So that reminded me what Mr. Xander said. It reminded me of that novel, and it went along some time, but of course at some point the house rotted away and just crushed down. Everything was gone. And on the other hand, their family in California, they had no water at all. The Florida were drowning. Climate fiction, extrapolating our current climate solution, very interesting science fiction genre, near future. For today, rainwater picks up soil, transports it down somewhere, and then the water evaporates and deposits the soil. So we have that in the sea, for instance, and it's actually flattening out the earth at some point, but it takes so long that it will take some time. So the actual algorithm is simple but slow. It's very memory intensive. You have a terrain map. You have to know the height of each point of the terrain. You have a water table. You have to know where the water is in your simulation. And you have a sediment table, which is how much soil is on the move, because you have to solve the soil in the water. So a lot of tables. The parameters would be, you have the amount of rain, so how much is raining down every iteration or every nth iteration. You have the solubility, which means how much soil is eroded in 1 unit of water. You have the evaporation, what percentage of water evaporates each iteration. And you have the capacity, so how much sediment 1 unit of water can hold. Okay, so a lot of different things, but it's very, very much simplified. So what is the algorithm? And as always, simple algorithm, hard to implement, as always, so many unknowns. But the 4 basic steps are rainfall, rain is coming down. You add a rain amount to the water table. Erosion, you move solubility water pixel into the sediment table. So taking away sediment from the earth, moving it to the sediment table. Then you move the water and the sediment downhill. And in the evaporation step, you deposit the sediment on the soil table and remove the water from the water table. So basically pretty easy to explain. But there are several things to consider. For instance, the rainfall. Depending on the simulation scheme, the rainfall can come down. The rain can come down every nth iteration and can be 1 or more. So it rains every 10th iteration, for instance. For the erosion, you actually have to make sure that some things are closed loop. For instance, sediment. You cannot just add sediment. It doesn't just come up from somewhere. Then, of course, the water, at some point, the water should evaporate. And this also should there shouldn't be more evaporation than water. And there shouldn't be water filling up the earth at some point, because this is kind of closed. And, of course, you shouldn't exceed the maximum sediment the water can erode per iteration. So there are a lot of maximums there, and they're easy to exceed. Movement is kind of the most critical part. If you remember the thermal erosion with the 4 neighborhood and the 8 neighborhood, so where to deposit, or where does the water actually go down? And if we have an 8 neighborhood, of course, yeah, then of course all the streams would run down either in a 90, 180, 0, or 45 degree factor. And so we can move it along the gradient. That would be one option. We can move it to the lowest pixel in the neighborhood. We can move it in parts to all pixels that are lower, just splitting it up. What is the actual height? just the terrain for visualization purposes, just the terrain plus the water level, or the terrain plus the water level plus the sediment. So a lot of open questions, and of course I have more than one implementation. So the evaporation is really easy to implement, like the water table evaporates at some point, but at some point also you have to take care that there can be a minimum amount of water, yet another parameter. Then you have water pooling at the lower ends of your terrain. You can think of a closed water loop, so it can only rain what evaporates. So you just add an amount of rain to your simulation and then say, oh, there is no more water than that, and just rain what's evaporating. And you can evaporate a fraction or a fixed amount. That's also not clear in the sources I've used. Yeah, and now let's take a look at the different implementations. They're here. Mazes, and then we have this thingy we can revert. I'm just clearing up here again, of course, and yeah, so that would be the hydraulic erosion with the gradient, where basically you have this rain amount, you have the solubility, you have evaporation, capacity, iterations, you have a terrain table, you have a water table, and you have a sediment table. Okay, definitely should look into my shortcuts. Otherwise, oh, that is good. That doesn't work. It's the same shortcuts as Google Docs, but no, it's not the same. Anyway, no, it works. I got it. Yeah, create the height map. Creating the height map is practically really easy. Where is it? Oh, I'm actually in an editor, so I can click it. Create the height map. We have a noise and use that. The easy version of it. Then we put it in the buffer in original noise to actually switch it. That's nice because then we can see what changed. And yeah, draw. We create an image of the whole thing and just paint it much faster. And yeah, erode height map, that's it. We have the water table, we have the sediment table, and the water moved and the sediment table. So we have actually a lot of data here, and then we move stuff around. So it's completely well documented, of course. So the water table gets this rain amount, and then we have the eroded sediment per x and y, add it to the sediment table and remove it from the terrain table. So we're moving it around. That would be here. And then we get the gradient. The gradient is actually really easy. So the gradient descent, machine learning, stuff like that, that's basically the same thing. So we want to know the direction where to go with the water. So the direction of where the water flows down, which makes sense if you think about it, because that's what's happened. The water is basically going always down. Yeah, it's really easy to really easy to find. Yeah, don't go into the detail, but anyway, you get a vector which gives you the gradient, and then we want the amount. We want to normalize it, so we get the direction, and then based on this direction, we define where to go and set it up. These are the possible directions: -1, 0, -1, -1, 0, -1, and so on and so on. And then we move it around. At the end, evaporated update. So we have an overflow here and evaporate the stuff. Where is it? Here's evaporation, and that's where we have the sediment. Okay, long talk. We want to see stuff, of course. Now it's opening up here, yes. So, and I really like that one because something is really wrong with it. So many lines of code. It makes these nice little warm things. So that's the original noise. That's the wormy stuff. Might be the case that I'm missing the up and down stuff. So these are all small rinselets maybe. It gives a very nice texture, I think. So that's the original noise. That's the hydraulic erosion. Look how it works out. Obviously, it's very pointed where the water moves. And we have a lot of these small ridges, which then give you this worm-like structure. So of course, in this case, it would be nice to have thermal erosion, which removes these ridges again. That'd be very nice. And yes, a depth map for wool shader, render sheep. That's a good point. I basically think that many of those PCG things were done by accident. And just not that you get the idea that this is something I sat down and coded in half an hour. I mean, I did, but then it took me kind of a day to set the parameters right. Because if you fool around with the parameters, this whole crazy thing goes haywire. So wait, I can show you that. That's fun. I like it a lot. So that would be our version here. And we can fool around with the parameters, of course. Like for instance, we want to have a solubility of 0.5 and see what happens. One element of water can take half an element of stuff. Doesn't change too much. We can go 0.9. It's moving a lot. It's faster. Playing around with parameters for this is both the biggest curse and blessing of game development. You're right, lover. That's the fun part. Yeah, it gets more sheepy. Let's remove this one too. We can evaporate a lot of water, like 99%. See what happens. Now it's much slower. Yeah, but the sheep texture is coming out again. That actually looks better. Maybe I should leave it at that point. Yeah, but you can see the difference. Let's go for 0.75 maybe. And it doesn't flow that far, the water. Now I get these long strands again. And of course we can remove the capacity, say 0.5 instead of 2. And then it will transport less water. Gives us again the strands, but light mode attract bugs. Yeah, maybe, but I'm not on the dark side. I'm not on the dark side. That's the problem. Okay, so you can fool around with the parameters yourself. It's actually huge fun to make this go crazy. So then we have a minimum height. Let's see. Close this one, close that one. That the water is basically, where is the erode function? Erode height map, yes. The water is changed differently, so you compute the movement direction, and depending on where it actually goes, we don't use the gradient anymore. So let's see what that looks like. So just changing the just changing the mode on how to compute the direction the water goes instead of gradient. We're using the minimum height, so where it actually goes, the pixel with the minimum height, and you can see it's totally different already. It gives us those pointy plateau-like bands here at some point, which is in itself rather interesting. Kind of blurring stuff out. Of course, we can fool around with the parameters to make it go haywire in a way. So we have more or less rain amount, how much soil, maybe heat that up a little bit. Yeah, then I totally get these moving around pixels. Go for 33. I think this is just added up sediment that is moving around like crazy. I had it with 0.5, I think. And we can evaporate, of course, more. That will, of course, take much longer. Yeah, it kind of blurs out the image, but basically does the same stuff. Okay. Then, of course, we can go and distribute the stuff instead of just moving it along the gradient or moving it to the minimum pixel. In the 8 neighborhood, we can distribute the soil. And that again looks different, of course. And what I now did is I added this water visualization. So the water is visualized in blue, and if there's a lot of water, everything is blue. And this actually looks good in a way that it does what we wanted it to do. Kind of, it makes these canyons washed out. So that seems to be a good approach. The only problem is that there is these black points, kind of extremum, which creates completely washed out soil, which should not happen at all. Let's take a look at the how much rain. 12, and where is the erode rainfall? Oh yes, then here it rains every 10th iteration. It rains 12, so it's obviously too much, kind of. And yeah, it evaporates a lot more than that. Okay, so we can fool around with that and have, for instance, something like we want to have 8 and evaporate, say, 0.93 and see what that does. That oversaturates stuff. Of course, as you can see, it's getting blue, getting really blue. So there's a lot of water in there. That's why I also added the whole water visualization stuff. Okay, so again, you can still have fun by adding the capacity, so how much water will be there, how much will be deposited. For instance, if the water doesn't move, we should deposit a lot. Maybe that's the problem with the black points here. Let's try it. No, it's not. Anyway, it looks cool because it gives you these washed out canyons from the side of the hill. So there's the hill, and you see there's something washing out. There's something washing out. So that's actually pretty cool. Okay, still unsolved. Dark points. A bug. Maybe it comes from the dark side. And finally, final sketch would be with a closed water loop. So, which means that we actually have amount of rain, but what we want is we only water the stuff with the water we have. So if evaporated water is smaller than 1, then we add the rain amount. Otherwise, we'll actually just add what we have here. So not adding any additional water. Let's see how that works out. It can only rain what evaporates. It's pooling, yes, but the pools, as they are, there's always the same amount of water. It washes down into the sea, or it actually should. That is something that is kind of weird here. Of course, there is more blue in this area, but not in this one. So kind of washing out, blurring out, more like islands instead of canyons. Yeah, but of course, again, we can fool around here with all the parameters. We can evaporate faster, for instance. We had that already. We can deposit more. First rain, yes. And it went unstable, obviously. It looks different. Nice enough. Change the evaporation back to 75. See what that makes. Oh yes, now there is some movement here. Yeah, so as you can see, this is not completely robust and stable. The parameters kind of lead to very different results. Now without the water, this also looks blurred out like the first version with the gradient. No, not with the gradient, the second one with the minimum height. The gradient still beats everything with the sheep texture. there's a lot of things you can fool around and have fun with. So, of course, that would be a very nice project. Being the god of landscapes in XR and then pointing at saying, add more water, something like that. Yeah, so how to actually create then terrain? Terrain you typically create by noise. So depending on what you want to do is Wally noise, of course, makes very nice hills. So if you want to have like 7-8 hills, then you know how to configure the Wally noise for that. And then just add a few octaves of Pelly noise for the details. Then you can mix and match thermal and inverse thermal erosions and hydraulic erosions, make a tool chain and configure it and see if something comes out of that. So it's actually pretty hard. There are cool implementations by other people too, so also worth looking at. And of course, triangulation is still a thing. So we can talk about this one also for the whole semester, but I'll leave it at that, because what I want to do is I want to grow stuff. I want to do vegetation. And for that, I'll just go into L systems. Funny enough, this already has been implemented in VR by Sebastian from Fire Totem Games. He made this nice little game where you can tend to bonsais, and he created the bonsais with an L system. And yeah, that's actually not so hard. I'm doing everything in 2D here, but of course it's extendable to 3D. Also one thing I should do at some point, implementing it in Babylon or 3JS. Okay, so L systems, you've learned to like them already with the zombie menu grammar, and but what you can do is you can expand stuff like A expands to AB and B expands to A, and then starting with the symbol A, you can expand A to AB, you can expand A to AB again, and B to A, or kind of something like that, and then it basically grows. So at some point they came up with these bracketed L systems, and I don't know if you remember Turtle graphics. I mean, that was even before my time. Turtle graphics. So that was a way of creating graphics with move turtle and then turn around turtle. So what you do, you have a pointer, which was the turtle, and you can move the turtle, and if the turtle move was used with a stroke, then it would draw a line. Then you can turn the turtle and then move again, and then it would add a line there. And that is actually what these things do, is F would be moved forward, and plus minus would mean turn left or turn right. And then you can rewrite this L system F to F minus F, F plus F, F. And then running it several times, you'll see that something like that comes out of that, and that totally looks like something growing, bush or a tree or something like that. So yeah, that's what we do with P5.js now and JavaScript. So we define a tree as a list of branches. At some point you have to be abstract, a list of branches. And we start with the stem and then add recursively. So we have a tree, iteration 0, we want to grow it in some direction. We have a start position and an end position for each branch. And then we put a branch on there, like here, the start and the end, and the direction, the grow direction. And then we split the branch kind of from the end position towards this grow direction. So if it grows upwards, we split the branch, kind of, now it goes there. And then we just add recursively. This would be the split branch, which is called ones. And then basically you split it left side. We have grow direction, which we turn, of course, if it's on the left side, we turn it to the left. Watch. Left, no, it's on the right camera thingy. Here. left. No, it's left. Then the direction goes here. So the grow direction is in this direction, not upward anymore. Okay, this direction. And for the other side, of course, here, so it doesn't go straight up, but it has a new grow direction. So we find a new grow direction, then we go into that direction, a certain length, and we have a new end position. So the end position before that would be the start point, and we push it to the tree. Start point, end point, and grow direction. End position, level plus one gives us the level, and also the right side. So for each split branch here, we call it twice in the method. So that also means it's recursive. At some point, we need to define where to stop, and we make it stop at a certain level, level 4, then we return. Then we draw the whole thing. We make a stroke in branch color. Brown tree branches are typically brown. This actually looks like a tree, and no, the Besenginster. But here we start with the line for each branch, from branch start to branch end. Then we create this nice little thingy. But let's look into that from the source code perspective. It's here. Closing this one, closing this and this, and then having this simple L system. Simple L system. Yeah, it's basically the same as I had on the whole slides. And taking a look at that, doesn't work. Hitting F12. What's wrong? Nobody knows. Let's see if it's still here in the editor. Here we are. Here we have the sketch. Using this sketch, putting it into the editor here. And see if it works. Yes, it works in the editor. Okay, that looks a little bit better because we can use it in here. And we can have fun by making it return after 3 levels. Or, of course, after 42 levels. Why not? Oh, I hope I didn't crush my computer. Oh, now that's good. Of course, now. What did I do? Classical. Created a recursive function and told it to go to an unmanageable amount of recursions here. So maybe not 42, maybe go to 6. Yes. Or 7. Yeah, and as you can see, it grows into itself, so it's not an ideal solution. So what would be next? Reduce the weight based on the growth and make it smaller. So instead of just going straight forward, we might use this branch weight and actually make the branch a third smaller for each iteration, and then we should end up with something like that. Let's see where this one is. With branch weight, I'll just copy it over again to the editor, and it looks a little bit better already. As you can see, we can also fool around and say we want to have it half, 0.4. Oh, that looks nice. Or 0.75, 4. Yeah, that's longer. So again, you have to actually find which parameters are good for you by fooling around with it. And again, here it grows into itself. What else? We can induce some randomness in the split. That's actually pretty cool. Copy it over. Randomness in the split. And then it grows into certain directions. And of course we can have fun here. Like here the random split would be not so big, 0.2 in polar coordinates. So let's make it bigger. And I really want to have the branch weight differently. Where's my branch length? Yes, but I want the branch weight differently. Rotate branch weight, minimum weight. Oh, it's based on the split. Okay. Yeah. That's the point. I won't figure that one out right now, but you get the basic idea. And that would be let them branch out slower with 1 point. Oh, that's it. Okay. Branch out slower. I didn't do that very well. Go direction. I have to put it up here too. I think at least. Oh, nice. That actually gives a very nice idea. Now it leans to the left. 1 minus split times 1.5. Oh, that looks nice. Isn't that nice? I didn't expect that this goes that way, but it looks cool. Yeah, the hairy tree. Hello, Mr. Hairy Tree. Very good. Okay, but as you can see, you can have a lot of fun. And branch versus stem, two different things. Yeah, that's the thing I thought I wanted to have. So that would be this one. And there we can have fun with that. Okay, so now we actually have this make it stop at a certain level. This would be this one. Then the alpha gives us the randomness, what we want to have in a certain area between 0.1 and 0.3. And here we can have the stem weight and the branch weight. And then we have the stem angle and the branch angle. So just having one stem that goes forward and one that branches off. So as you can see here would be the stem and this would be a branch, but after branching off, this would be the stem. So the smaller one would be the stem, the branch, and then we get this kind of cracks here. Also, if you look at that, that would be really nice to have as a to have as a kind of height map thingy in the as a river or something like that, the river Amazon. And there we can actually have a lot of fun, like having this to 1.5. No, it doesn't work. 1.2 was the original one. What did I break? 1.1 maybe. Yeah, that the Stumpy tree. Meet Stumpy, our new tree. 1.3 would be first. No, out of range again. Oh, it's not very robust what I programmed here. Oh, it definitely seems that. Yeah. Ah, you can feel it. It's nice. Branch weight maybe 1.8. That works. And it gives us these nice trees. Wains, yes, that's right. That's right, it's Wains. And we're back to the zombie apocalypse again. Also the brown is kind of Wayne red. Yeah, so that's rather easy. You can also go into 3D. That's also a possibility. And what I really like is if you just interpret the very last branch, or the very last branch and very last stem as a leaf, and then you can get this very nice, very nice effect of having leaves on the tree. And I'm extremely lazy. I just made triangles and said it's a ginkgo tree. And of course I animated it, because why not? And I'm actually pretty proud of that, because this already gives you a lot of stuff for games. So you can actually use this already to create trees for games. For instance, in a background of a 2D scroller or something like that, and they're really fast and easy to generate. So one thing you can additionally do is you can check if they're to your liking. I mean, this one, for instance, the leaves touch the ground here. You can sort this one out with a test and generate routine, so that would work out. And of course, you can change the parameters, because it's always fun to change the parameters. Minimum weight 0.25, and this should have many more leaves. Yes. Or less leaves. We can give it less branch weight, then its stump here. We'll make it longer. And of course we can fool around with the splits here. And if it accepts 2, yes. And yeah. That totally exceeds, of course, our our painting canvas. Yeah, anyway, a lot of fun stuff to do. Test and generate would be a good idea, because then the trees would not grow out of the picture or be uneven or look like they would be falling down after the first storm. But it gives actually, no, this one not, but typically it gives a rather balanced version of a tree. So that's actually pretty cool. So this one is rather balanced. Okay, just a few things to add up stuff, that we don't only talk about the L systems. So what you can also do is you can do space colonization for tree growing. So what you do is you create a volume, and 2D it would be something like a circle or a triangle for a tree or a needle tree. And then you define the leaves first, or the ends of the branches, the twigs, and their attraction points where the branches grow towards. Of course, they cannot grow into each other, so they would grow around each other. But as soon as a point of interest is reached, it gets removed. If multiple points of reach are in range, points of interest are in range, then the tree branches split. So there is a link to it. You can actually try it out yourself to implement. I didn't go into that because that already sounds like, oh my god, so many parameters. How do I ever get this one stable again? Okay, I tried to start Blender at the other end, but my Windows kind of does not like me too much right now. What else can you do? You can actually create something with a particle system. I'm not sure if I have it installed. I'm most likely not, but I can do it really fast if it's still here. Edit preferences, add-ons, sapling tree gen. Yeah, so basically if you have Blender, then you have to add this sapling tree gen stuff, and then you can add a tree in Blender. Go there. Shift A, there should be the tree at some point in curve, sapling tree gen. Yeah, here we are. And you can configure it here. Load preset, small pine. Oh, nice. Here we are, small maple. I like that. I just used a small maple. And like that. And then we change the seed. Yeah, that looks good. I like that tree. And what we can then do is we can actually add particles to it. I haven't done that for some time. I'm not sure if I can do it the way I want to do it right now. No, maybe I have to try it on another day. What I need to do first is basically create or make a mesh out of it. Yeah, as I said, haven't done this for some time, so it would be searching and searching like crazy. But yeah, basically meshing it. And then you can add the leaves as particles. That's what I did here. Of course, that can go better. There is this new. Oh, okay, let's not try that. There's the new hair system. That might be your thing. But now there is this grooming interface. What you can also do is you can use everything in Blender with geometry nodes. So there is this, maybe I find it, that would be actually pretty fun to show it to you. Should be here. Algorithms, Blender, procedural water. Oh, I only have the result. But using geometry nodes, you can create stuff like this one, that is procedural water in Blender. So the water is moving around. What it actually does, it's a height map that is changing over time and leaving a bit of the impression that this is water. And just to give you something to play, which is kind of unrelated because it's a template-based system. You can create ships also with animation. With this tool, it's called the ship mixer. And Kenny has several other things, like for instance, the creature mixer and the avatar mixer. Let's use the avatar mixer for PCG, for procedurally generated content. And that's actually pretty nice because it gives you a lot of different possible avatars which you can integrate in your game, also ships. So yeah, pretty cool. Yeah, that's basically it for today. I hope there was something in there for you. So what you should definitely remember is that oh no, wait. So now I need you to stay awake for a second. I think I forgot something. Have you heard about the marching cubes algorithm? Maybe not. Marching cubes. Marching cubes. Because I think that I have, but not in this link. Ah, that's good. Okay, thank you very much, Mr. Xonte. Solves the problem for me. Because what I did is, after saying that we have this shader as a texture and the exercise Poly noise shader, I totally forgot that I wanted to show you the marching cube or the marching squares algorithm. Yeah. So this is also something that fits in kind of with the terrains. So that's what I wanted to add here. That's part of the noise stuff. So if you have a noise map, but you don't want to have the noise map with this quantized thing, which is kind of uncontrollable, but you really want to have the levels in control, then you can use the marching squares algorithm. So what it does, it creates a contour from a 2D scalar field, and there you can put in whatever you want, for instance, poly noise. And it's basically the same as the marching cubes algorithm, but in 2D. So, and that's what I just wanted to show you for the last 10 minutes. So you have a scalar field. So each dot in here denotes a value. What you do is using this value, you create stuff. That's the fun part. In our case, we're doing it in a binary way. So we have zeros and ones, like the white ones would be the zeros and the black ones would be the ones. And using them, we can actually have the corners. So in here, there would be 4 white corners. Here we would have 2 white corners and 2 black corners. We actually, for the binary version, we only have a certain amount of possibilities. There would be case 0, where all of them are 0, case 1, where this one is 1, and this is 4 times in there, like here, 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 and once more here. So 1, 4, 2, and 8 are rotated. Then we have 2 to the lower level, 2 to the upper level, and 2 to the side, left and right. 4 cases more. Then we have the full case, all of them are 1. And then we have these 3 are 1, and the diagonals. So case 10 here. And each of these cases can be handled separately. And what we then can do, we can create for each of those cases an image and just add them together. So we determine the case here, and then we paint the contours. And yeah, we have A, AB, AD, BC, and CD, and just create the rectangles with paint and fill shapes. And that's what it looks like then. So this would be already a nice animation based on the 3rd dimension of poly noise. But you basically get the idea. It might be something like a 3-dimensional cave system. And gives actually a very cool impression. Also well used in games. So just to have you up to date on this one. There's also, oh, I'm logged in, that is good. That is very good. Somewhere here. Watching squares. Let's see. Ah, yeah. Here we have the points. So you can actually see what the points do. So the black ones give you the light color, and the white ones give you the dark color. And let's see what that do. Ah, okay, that's the one with the movement in here. Okay, yeah, that was what I wanted to add, because I also have it in the slides and I didn't want to miss out on that. So next time we're going to, and that is kind of a break in session, we're going towards Sudoku. On the one hand, because I really like Sudoku. On the other hand, because I want to do wave function collapse, which I nearly have finished in my slides. Wave function collapse is a very prominent algorithm which gives great output for tile maps and other stuff. You can also use it in 3D. Yeah, for that we actually need a little bit of understanding of Sudoku. And then I thought, oh, what the hell? Let's just make a course about how to create Sudokus, because that's also fun. And puzzle is also a thing that is PC-like. So next time, Sudoku and wave function collapse. Okay, so if there are no more questions, I'll stop the stream, but I'll stop recording anyway. I have 3 questions about the 3D maze. Should I ask you here or by email? I'll stop. Yeah, ask me about the 3D maze. Anyway, so if you type it in, I can try to answer it. Take some time, of course, until my word reaches you. First of all, if I make a game, is it necessary to be able to display the maze from above in order to see the generation? No, you can just end up with a maze in there. I mean, you should kind of create the maze yourself, but you can create it once and then just import it if you want. But of course, if you want to see the generation, oh, awesome, but not necessary. Secondly, are we allowed to use free asset if I had a link to it? Yes, so that's also what I encourage. If you're creating games and you want some eye candy, then please use free assets. Kenny is definitely a thing. So Kenny, I always recommend to take a look at the stuff Kenny makes, because Kenny gives you a lot of free stuff for 3D, for 2D, and so on. Oh, okay, there are starter kits for Godot. I changed a lot. So go there, get the stuff, make your game look nice. Everything looks a little bit like Kenny's games, but very cool. Finally, if I make it with Unity, should I submit? Do I need to return a link to the game hosted by me, or the game build, or the source code, or all 3? It would be nice if you have something to upload, maybe upload the source code and the Windows X, and I would really appreciate if you add a link where I just click and then can play it in the browser, not running a Windows program. That'd be nice. If you upload a web build, I know that this often is kind of problematic because it doesn't run on my end. Not because I'm not able to run a local server, but because, I don't know, so many errors. Some of them I can actually fix because I know them already, but it's much better if you just upload it by itch.io, and then in itch.io you can actually hide stuff. Let's see if I show you stuff. I just have to move it here because I'm not sure if I'm showing you stuff you don't, that is against the GDPR. Upload new project, view profile. This is my library, maybe. Doesn't work too well, my purchase. Posts. No, dashboard. That is crazy. Okay, let's use the dashboard. So you can upload a game like this one as a draft and then just share it to other people. Let's see it, more information. There's a secret URL here, and then you can send me the secret URL and you can basically run the game. Or I can run the game. That would be the whole idea. That's a Godot game. I'm missing out on the. It's a German game, Boulderwürfel, also because there's a lot of text, and I can actually check the die and then roll the die, and then it will give you what you have to do. Bouldering without hands. That's really nice. If I get it running on the mobile phone, because that's what it was meant for climbing training. It's a mobile phone game. But then I'll definitely translate it to English too. But what I actually wanted to show is that you can just upload the draft and you have the secret URL and send it to me. That would actually work. Also, you get well versed in itch.io, which you need for the game jam. Anyway, can we use any algorithm to generate the maze? Yes, yes, of course you can create it with any algorithm. So we had a lot of them. I missed out on recursive backtracking. You can try out this one too. I also have a private server, so I can use it. Thank you. Yeah, okay, great. So you can upload it on your server. Okay, I hope that answers most of the questions, and I say goodbye to the people that are here with the recording. Bye.